Okay, we're here with our student Rita to talk about interpreting nonlinear expressions. Ready to go, Rita?
Yeah.
Okay, great. So let's just understand what this means. Interpreting means to understand the different pieces and parts and what they mean. Okay?
Okay.
And a nonlinear expression, is an expression that doesn't describe a line. So we're going to be talking about things that describe curves, and basically it's going to be quadratics and exponential, and we'll look at two forms of exponential, okay?
Okay.
All right, so let's first talk about a quadratic expression here. So this is a common use of quadratics. It's called projectile motion. A projectile is something that flies through the air like a bullet or a ball or something like that. So here we have height of a ball thrown in the air from a balcony. So if you imagine you're standing on a balcony, you're going to throw the ball up in the air, and its height is defined by this expression here. Okay?
Okay.
And it might go up for a while, and then it'll fall for a while. And if you were to plug different values in for t, what t stands for time here, then you would be able to figure out the height. Okay? So let me ask you this. What is the starting height of the ball? And I don't know if that will be obvious to you, so let me give you a clue here. If we were at the start of our experiment here, what does time equal? Does it equal 10 seconds in, or 5 seconds in, or 40 minutes in? What does time equal at the start?
0.
0, right?
Yeah.
So when we do an experiment, it hasn't started yet, so time is 0, and then we'll hit the stopwatch when we start the experiment. So if time is 0, we can put 0 in for t here, and 0 in for t here. Well, what's going to happen to those two terms?
They go away.
Yeah, they're going to go away, right? So 0 and 0, that's going to go away. So the starting height of the ball is what?
41.
41. So in a quadratic expression like this, that's describing a ball or some other thing in the air, projectile motion, or anything really, if t is time, then that is the starting, then this term over here is the starting value. Okay?
Okay.
So the ball's starting height is 41 feet, which means you're standing on a balcony that's somewhere around 41 feet. You know, the ball itself is at 41 feet. Maybe it's down at the balcony's a little lower because you're standing on it. But then we can also ask ourselves an important question that we should ask about any expression, which is what changes when the variable t changes? Okay, so let's look up at here. Will the first term change if t changes?
Yeah.
Yeah. How about the second term?
Yeah.
And how about the third term?
No.
No, because the third term doesn't have anything to do with t. So we can say that terms 1 and 2 change, but not term 3. And we know that term 3 is what?
The starting point. 41.
The starting height, right?
Mm-hmm.
So we can say the starting height doesn't change as t changes. And that makes sense, right? If we're standing on the balcony, the height of the balcony isn't going to change as t changes. But the rest of the things will change in a quadratic expression. Okay, so that's a quadratic expression. Let's move over to exponential expressions. We're going to look at two forms here. So the population, and this is, I'll just pause right there. Populations are often described by exponential expressions, like what we're going to look at here, okay? That's just how the nature works, that things grow or shrink when you're talking about the population of something through an exponential expression often. So the population of bacteria in a lab, or deer in a park, or people in a city, or whatever is described by this expression here. And the reason we call it an exponential expression is look where the variable is. It's in the exponent. So that's what exponential expression means. It's much different than over here or a linear equation or expression. So now I'm going to ask the same question. What is the starting population? So to find the starting population over here, what do we do?
We put in 0 for t.
Right, so same thing here. So we put in 0 for t over here. We have this parenthetical here, 1.03 to the 0 power. But what's anything to the 0 power?
1.
1, right? So then we just have 372 times 1. So what's the starting population?
372.
372, right? So in any exponential expression like this, the number that's out here in front of the parentheses is the starting population, right?
Right.
Okay, so that makes it really easy. Kind of like with quadratics, you can just look at that third term and know it's the starting height. This is the starting population. Okay, so let's ask ourselves the same question we did over here. What changes as the variable t changes? And the answer to that is not the starting population, right? As t changes, this part will change, but the starting population out here doesn't change as t changes, right?
Right.
Okay. Now let's look over here at the different form of the exponential. It's the exact same thing, but we're just splitting that 1.03 that's in the parentheses out into two parts. 1 plus 0.03. And there's a reason that we're going to do that. But again, this is you could use this for any sort of population of bacteria or deer or people or trees or whatever. So let's ask ourselves, what is the starting population? Well, the same thing happens here. We're going to put in 0, and that whole parenthetical stuff is to the 0 power. So again, it just goes to 1. So the starting population is 372. Does that make sense?
Yeah.
Okay. Now the reason, though, that we split out this 1 and the 0.03 is because if we were just to multiply the starting population by 1 to any power, it would just stay the same, right?
Right.
Okay. So what we're doing here is we're splitting out this part that's different than 1. And that turns out to be the percent rate of change. Okay. So what we're talking about is splitting this out so we can understand the percent rate of change. It's 0.03. If we turn that into a percent, what's that as a percent?
3%.
3%, right? So 0.03 or 3% is our percent rate of change. That's why we'd go to the trouble of writing out this longer version. It's harder to write this out than it is to write this, but this tells us really easily what the percent rate of change is, okay?
Okay.
And now let's ask ourselves the same question. What changes as the variable t changes? Well, does the starting population change?
No.
No. So same thing as over here. Starting population isn't going to change as t changes. And here's another thing that doesn't change. The percent rate of change does not change. This whole parenthetical portion, this factor will change as t changes, but the 0.03 won't change. And that's how you can say stuff like, well, the bacteria population is growing at 3% a week or a month or whatever t is in. Or the deer population in the national park is growing at 3% a year. And that's why we break this out, and that's how something can grow at a steady rate, and you can see it in the equation because that's not changing as t is changing. Does that make sense?
Yeah.
All right, great.